Hello and welcome to another exciting chapter in statistics, which we deal with in chapter 11. Again, this is Professor Naragon bringing you now the two sample tests of hypothesis. So, we decided to bump it up a notch and do two instead of one, like in chapter 10. So, will this become more difficult? Or, with the vast knowledge that we already know, help out? Well, let's find out. So, of course, first step that we run into is a poorly done slide by them, but our learning objectives. So, learning objective number 1, we're going to be looking at testing a hypothesis with two independent populations means are equal, assuming that the population standard deviations are known and equal. Then, learning objective number 2 is going to test the hypothesis that two independent populations means are equal with unknown population standard deviations, because of course we always do known and unknown. Number 3, we're going to test a hypothesis about the mean population difference between paired or dependent observations. Okay. And then finally, we're going to explain the difference between those two samples of dependent and independent. That is right there in the copyright of McGraw-Hill. No, lovely. So, comparing two populations means, so when we compare the two populations, we're going to wish to know whether the means could be equal. We're going to investigate whether the distribution of the difference between the means could have a mean of 0. What does this mean? It's probably we're going to have a lot of formulas. Why? Because it's statistics, it's math. That's why. Anyway. So they give a couple of examples, like, is there a difference in the mean value of residential real estate sold by male agents and female agents in South Florida? Is there an increase in production rate after music is piped into the production area? So again, we're looking to see if we can figure out, is there really a relationship between the two? And how does it work? Well, let's go. So, we can use the following formulas to compute our z. As soon as you hear z, you definitely know this is known standard deviation, right? Because it's always t when we use unknown standard deviation. Okay? So, we're going to compute z if the following conditions are met. The two populations follow normal distributions. The samples are from independent, unrelated populations. That's going to be key. The population standard deviations are known. Yes. And it pops up this fun formula, which I kind of wish they expanded more, showed more on. But it's going to be z equal x bar 1 minus x bar 2. So there's our two samples. And then, as you can see down below, looks like we're going to have standard deviation squared plus divided by the sample size or population size, since it's z. Either way, 1, and then we do the same for the second sample, or population. Sorry, gotta keep it with population, and we're going to add those two together, and square root them. Don't forget that square root. Lots of square roots. Yeah. All right. And then with independent populations, the distribution of the differences has a variance. Again, standard deviation squared equal to the sum of the two individual variances. Okay, cool. Basically, that's what's inside the variance of distribution of differences in means. It's all fine and dandy, but wait till we get to the practice problems and actually start working them in this PowerPoint, huh? So let's start going through the example. All right. Customers at the Food Town supermarket have a choice when paying for their groceries. They may check out and pay using the standard cashier-assisted checkout, or they may now use the new Fastlane procedure, self-checkout. The store manager would like to know if the mean checkout time using the standard checkout method is longer than using the Fastlane. The time was measured from when the customer enters the line until all his or her bags are out in the cart. Well, at least they're using Food Town and not Walmart, which only has maybe 1 or 2 checkouts. But, sorry, I had to make a Walmart joke. Yes. Anyway. So, again, we're going to go through our steps here. In step 1, we're going to state the null and the alternative hypothesis. Okay. Basically, we're going to see if the mean of our regular standard checkout is less than or equal to the mean of the fast lane. Okay. Then we're going to have our alternative, which does the standard is greater than our fast lane. So again, we're going to see by alternative, which is actually in the question, is the standard longer than our fast lane. We're going to select the level of significance. Okay, again, we're going to decide to use 0.01 and then determine the test statistic we'll use Z since the population standard deviations are known. We already know this. We are awesome at this now. So, after chapter 10, I believe y'all are awesome at figuring out which one we use, either Z or T. Alright, and since we definitely know there's no equal sign, it's not equal, not equal, we have the less than, greater than, then we're dealing with one tail. Okay, so formulate the decision rule. We're going to reject the null if Z is greater than 2.326. Basically, again, in the tail. All of a sudden, it's like, Again, we figure this out because this is a one tail and using our significant level of significance of 0.01. So some of these, again, I'm not going to go through the complete step because we've already done it in chapter 10. We did the complete step again, like you see, in the practice problems. But it is 2.326. Fun. Next, we're going to calculate. Everybody just went, wow. It's like the sign of, oh my God, that looks crazy. Don't worry. It's fine. Okay. So again, Food Town is going to randomly select 50 customers. This is added on to our problem right here. Okay. From the 50, customers using the standard checkout and compare a mean time of 5.5 minutes. Okay. And they have selected 100 customers using the fast lane and computed a mean time of 5.3 minutes. Okay. So using our formula, R1, our first sample, is the standard. Okay. Again, this is the one that we're really comparing with. Oh. And then minus our fast length, which is sample 2. So 5.5 minus 5.3 be on top. That's our mean times. And then using the same approach, we're going to take standard deviation squared. So 0.40, which going through where the PowerPoint gave us standard deviation, because I know that's going to be a question, and they actually didn't. All right. Yeah, that's... So they're just... Apparently that was part of the problem that they didn't give us. They're just assuming standard deviation. That is not nice, guys. Okay, so we're going to assume the population standard deviations are 0.40 for our standard and 0.30 for our fast lane. Which again, it looks like we may have to actually calculate that later on. We'll check when we get into the practice problems. Because it seems like the book just decided we're going to assume this. Nice. Okay, anyway, we're going to take the standard deviation that we now know that they assumed is 0.4 squared divided by 50, because that is the random selected amount for standard checkout. And then we do the same for our fast lane. We're going to add them together in square root. Comes out to 0.064031. And divide it by that 0.2, we come out to 3.123. So the test statistic is greater than our critical value of 2.326. Therefore, our decision is to reject the null. Okay, it falls within the tail. So, interpreting through step 6, again, going through all 6 steps like in chapter 10, the difference of 0.20 minutes is too large to have occurrence by chance, so we conclude the fast lane method is faster. Nice. That still throws me off that they all of a sudden just assume that. I hide these PowerPoints sometimes. Okay, let's look at our good old t-value, which is coming up with unknown population standards. So there are 2 major differences in this test and the test that's described in this chapter. We assume the sample populations have equal but unknown standard deviations. So again, t-distribution. Which I just love that. The 3 requirements for this test. The sample populations are approximately normal distributed. The sample populations are independent from one another. Again, it has to be independent. The standard deviations of the 2 populations are equal. Okay. So remember the test right here is the 2 populations follow normal distributions, the samples are independent, and the standard deviations are known. Here, we have the standard deviations of the 2 populations are equal. Yeah. Okay. So, you ready for the formula? If you're not, oh well, here it is. Y'all thought the other one was going to look complicated. Here's a little bit more fun. Don't worry, we break it down. Okay, so finding the value of t requires two steps. Again, the first step is to actually pull the standard deviations according to the following formula. Remember, we assume that they're equal. So the pooled variance is going to take the sample size from our first one, minus 1, times s squared, so standard deviation, our sample deviation right there, sample standard deviation. Then we're going to do the same thing with our second population. So we're going to add our sample size minus 1 times standard sample standard deviation squared divided by our two sample sizes added together minus 2. I know it looks more complicated than what it is. Okay, I understand. Math is like that at times. Formulas takes a little bit. Remember, practice makes perfect, guys. So the value of t is computed using the following formula. We're going to take our means, so mean from our first sample minus our mean from the second sample, divided by the square root of our sample standard deviation from the pool variance, plus the fractions of 1 divided by our standard, our sample size for 1, and then plus 1 divided by our sample size from 2. Okay. And then look at degrees of freedom. Remember, t values have the good old degrees of freedom. Freedom from the test are n1 plus n2 minus 2. Okay, so the degrees of freedom should be the same as your pool variance denominator. Okay, it should be the same number. If they're not, then we're going to be calculating one of those wrong. But I mean, it's okay. Okay, it just brings in some more fun. So here's a sample. And notice already, we're going to know it's a two-tail. Okay? How do I know it's two-tail? Because we got equal signs already down here in our hypothesis. Okay? So, Owen's Lawn Care from Lone Star 911 manufactures and assembles lawnmowers that are shipped to dealers throughout the U.S. and Canada. 2 different procedures have been proposed for mounting the engine on the frame of the lawnmower. The Wells method and the Atkins method. Okay, that's 2 references to Rob Lowe right there. The question is there a difference in the methods, meaning mean time to mount the engines on the frame of the lawnmower? So, they're saying, is there a difference? No, it's not greater than or less than. So, we assume that they're equal, same time, or our alternative is that there is a difference. They're not equal. Okay? So, our level of significance, again, we're going to use 0.10. We're going to determine the test statistic. We'll use t since real population standard deviations are unknown. They are. So just like chapter 10 homework, we have to figure out the 2 tails. So we know right now the decision rule is we do not reject the null if t falls between negative 1.833 and 1.833. Again, the degrees of freedom. Let's take into the 2 sample sizes. So this is 1, 2, 3, 4, 5 plus our Atkins, which was 1, 2, 3, 4, 5, 6, which was 11 minus 2. So it would have been 9. Okay. Again, we're going to go through these sample sizes as we move forward. All right. So we're going to make the decision regarding null, and it takes 3 steps to compute the value of t. Okay. So calculate the sample standard deviation. Okay. So again, taking the average minus the average from each number and square, and add up to create our variance. Again, we're going to probably use a little bit easier with Excel as we move forward, but again, we're going to show you the basics so you can understand it just a tad bit. Next, pull the sample variances. Okay. So this is our first one. So we got to figure out our sample. So this is where they take the 34, which is right here, and divide by their sample size minus 1, square root it, which we get a 2.9. So there's our standard deviation for our W, Wells, and then we figure out the standard deviation for Atkins, doing the same method as we've done before. Okay, so again, both the standard deviations are known. Here, determine the value of t. Take our first sample minus our second, so 4 minus 5. And then the sample, I feel like they kind of skipped the formula right here. Yeah. It seems like something happened here where they skipped the actual S2. Okay. So, again, we're going to go through the formulas as we go through, but yeah. Alright. So calculator, I'm going to go back through each one. Make sure we get to the number that they're stating. So we would have so using our calculator, we'd have 4 times 2.9155 squared. I'm going to be going back and forth. Okay, so we're going to add it to the same thing. So, calculator. Plus, which was 5 minus, so that's 5 times 2.0976 squared. Okay, so that should be on numerator. Right? Yeah. Alright. Then it's divided by divide this by 5 plus 6 minus 2. And there we go. Okay? For some reason, they in the PowerPoint, they skipped that part, which is annoying in a way to show y'all how they get to determine the value of t We don't add the pool. So that's how they got to the pool. They did some rounding. But, alright. Alright. So, now we got 4 minus 5 divided by the square root of that 6.22 that I just showed you. Multiplied by 1 divided by 5 plus 1 divided by 6. And there we go. So we get negative 0.662. Now, the decision is not to reject the null because it falls in the region between the two. Okay, next. Interpret the data. Well, the results, we conclude that the sample data fail to show a difference between the two assembly times of the two methods. So they're practically the same. Okay. So, again, I hate that they kind of went from figuring out the standard deviations and then just jumped to the next one. So, that's the fun part of PowerPoints. Next, unequal population standard deviations. Oh Lord. If we cannot assume the population standard deviations are equal. So here we assume that they're equal. If they are not equal, we adjust the degrees of freedom and the formula for finding t. We're going to determine the degrees of freedom based on the following formula, which is the degrees of freedom will equal the standard deviation squared of 1 divided by the sample size plus the sample standard deviation of 2 squared, which is the second standard deviation second sample divided by, of course, its sample size, all squared, divided by the sample standard deviation of the first sample squared divided by its size squared divided by its size minus 1 plus the same thing for sample 2. Okay? And then the value of test statistic is computed from taking the difference of the two means and divided by the standard deviation of standard deviation of the first sample squared divided by its sample size plus, of course, the same thing for our sample 2. Which seems like a blast. It does. It gets a little easier. Okay? Again, once we start plugging in the numbers, it looks a little bit different unless the PowerPoint decides it's just going to skip the formula. I still can't believe it did that. So, why we do this? Well, in many cases, there is a reasonable assumption that there is an equal, but if there is not unreasonable to assume the population standard deviation are equal, then we use these formulas. And then we adjust the degrees of freedom downward using our formula right here. This results in a larger value of the test statistics for rejecting the null hypothesis. Yeah. So example. Personnel in a consumer testing laboratory are evaluating the absorbency of paper towels. They wish to compare a set of store brand towels to a similar group of name brand towels. For each brand, they dip a ply of the paper into a tub of fluid, allowing the paper to drain back into the vat for 2 minutes, and then evaluate the amount of liquid the paper has taken up from the vat. Okay, so this is sample 1, the same thing that we see on the commercials where they always show the absorption of 2 brands. A random sample of 9 store brand towels absorb amounts. is if so, and a random sample of 12 name brand towels absorptions as so. Okay, after observing there is more variation in the stored brand, it does not seem reasonable to assume the population standard deviations are equal. Okay, so we decide to use t distribution and assume the population standard deviations are not the same. So again, two-tail, typically that's what we're going to see. Are the time lanes the same? Since we are not putting it exactly as equal, we do have to calculate the stored name brand. So again, the two big things we want to take from the numbers is the mean, which they calculated, and the standard deviation. Next, we fit it all into our formula. So and then they do it this way, which looks like they have made a crazy error. Wait, no, I'm reading the wrong one. Sorry. It tells you sometimes I'm looking at the mean when it is standard deviation. I know it's standard. It's just eyes are flowing to the wrong one. So here's our standard deviation. Having too much fun here. Okay, guys. So standard deviation right here, and we plug it in. Again, sample 1. There's our 3.321. There's our sample 2, 1.621. And again, our sample sizes. And we'll just plug them in. And then we use our calculator to help calculate out the problem. So a lot of squaring going on. Square, square, then square that. Then square, square. So be careful and don't forget all those squares. It's good old square dancing going on. Okay, so after plugging all those numbers in the formula and into our calculator, we come out our degrees of freedom is 10.86. Okay, so because of that, we're going to use 10 as our degrees of freedom. We round down. So this means our values are going to be negative 1.812 and 1.812. Now we're going to basically calculate our items. So step 4, we're going to not reject the null if it falls between these two numbers, negative and positive, since this is a two-tail. Now we make the decision. We're going to calculate. Again, plugging in the numbers that we've already figured from the two charts. We got our means, and then we got our standard deviations. Again, once you plug it all in to figure out t, we come out to negative 2.474, which is does not fall between. So we are going to reject our null. And this means the mean absorption rate of the two types of towels is not the same. It's really all it goes with. You're like going, the formula itself. Oh my God. Yeah. This looks more complicated than what it is. That's the thing. When it pops you with all these letters, it will always look more complicated. That's always the fact. Okay, but we're going to break it down step by step in the practice. All right, dependent samples. When we first compute the mean and the standard deviation of the sample differences, the value of test statistic is computed with the following formula. So it's going to be t equals the mean of the differences between the pair of related observations. So we're going to have to do some subtraction here. Okay, SD is the standard deviation of the differences between the pair of related observations, and N is the number of paired observations. Okay. So our example, after the standard deviation of differences will be computed with the formula from 3-11, so chapter 3, way back then, except D is substituted for X. Okay, nothing too different from there. So our example, Nickel Savings and Loan employs two firms, Sadik Appraisals and Boyer Real Estate. I totally butchered that name. But anyway, it's all good. So, to appraise the value of the real estate on which it makes loans. To review the consistency of the two appraisal firms. Again, we typically already know, if you know how business works, appraisals and real estate typically are very closely together. They're not really independent from each other. So Nicola is going to randomly select 10 homes and have both of the firms appraise the values and select homes. Thus, there will be a pair of values for each home. These appraisal values are related to the home selected. This is called a paired sample. So, we know that Nickel Savings and Loans wishes to compare the two companies it uses to appraise the value of residential homes. Nickel Savings selected a sample of 10 residential properties and scheduled both firms for an appraisal. Okay, the results of the reporting in thousands are as follows with Shaddick and Boyer. And we're going to use a 0.05 significant level. We're going to conclude there is a difference between the firm's appraisal values. So again, a two-tail. So we're doing a lot of two-tails when we have the t-test. Okay? Probably already said that, but doesn't matter if I repeat. Anyway, step 2 is again our level of significance, which is the 0.05. Determine the test statistic. Again, we're going to be using t value. So that means our decision rule. We're going to reject if t is less than negative 2.262 or greater than. Again, we have a two-tailed test with 9-degree level of freedom because we're both using 10 residential properties. So 10 minus 1 is 9. Okay, nice. So here is the fun part. Again, a lot of it's easier just to put in Excel and do some formulas and move on. But we're going to find the difference between each one using each of the homes. And then we're going to compute our standard deviation. Okay. Next, we're going to make and base our decision. Now, the value of the test statistic is 3.305. Again, computing as we would have done before in prior chapters. And we come out to that it is greater than 2.262. So we're going to have to reject the null. So we can conclude there is a difference between the firm's mean appraisal home values. Okay. Whew. Sometimes I feel like I need a break while I'm reporting. Okay. I know y'all guys are enjoying this so much. It's okay. It's okay. Y'all got this. Y'all are going to be so smart at this statistic stuff. You'll be like going, oh, please let it be over soon. Almost. Still got one more unit. Okay, so dependent and independent samples. There are two types of dependent samples. The first first type of the samples is sometimes referred to as the before and after study, which of course our example with nickel saving and loan, we assume that we have two independent samples rather than dependent samples of real estate. We would have pulled the variance of samples and used the formula. But because we're using a before and after approach, basically they're dependent to each other. The hypothesis test based on dependent samples eliminates the variation between the values of the properties and focus only on the comparison in the two appraisals. Okay, so again, those characterized by measurement and intervention of some type and then another measurement. For example, suppose we wish to know that by playing music in the production area, we are able to increase production. Well, we begin by selecting a sample of workers and measure their output. Then we place a speaker in the production area and play soothing music, and then we again measure the output. Same workers. It's just it's all dependent on those workers. A matching or pairing of the observations again is our nickel and savings. We prefer a test based on dependent samples because it reduces the amount of the variations. Again, make a better test. Whew. Okay, so that's going to lead us to our practice problems. Y'all know the rules. Try to do the practice problem first. Get as far as you can on understanding before I explain it in the video. So pause each time, read the question, and then let's see how well you're doing it. All right, let's move on to our first question and see how we handle these formulas. So starting off with the first question, even though that they're different numbers, but so we have a sample of 40 observations is selected from one population with a population standard deviation of 5. The sample mean is 102. A sample of 50 observation is selected from a second population with a population standard deviation of 6. The sample mean is 99. Conduct the following test of hypothesis using the 0.04 significant level. Wow. Okay. So right away, we know this is a two-tailed test. Next, we gotta find Z. Okay. So with Z, right now we have a 0.04 significant level. So we need to take the 0.404 significant level. So let's get our calculator out. Oh, I already have the calculator out. Yeah, nice. So we're going to get the calculator out, and we're going to take 1 minus 0.04, which gives us 96. And since it's a two-tail, we're going to divide by 2. Mostly, we divide by 2 no matter what. So we get 0.48. Now, going to our table, right here, we need to find the closest to 0.48 without going over, which is right here. Okay, 0.4798, so that says 2.05. So 2.05 is our decision. So me see. I have to remember because I know I used it before. Here you go. So our z value equals to 2.05. So for our decision rule, we know that we're going to reject H O if z is less than 2.05 or if z is, wait, that should be the negative version. Yeah, negative 2.05 or z is greater than 2.05. Okay. Now it's time to compute our test statistic. Yay. So, for our test statistic, remember we're going to use, since it's one that we know of, we're going to use z all the way over here. So this fun one, okay? So in our calculator, we're going to take our first sample, which happens to be the 102 sample mean, 102, minus 99, which was our second sample mean, and we're going to divide this by, let's see, try and think how to do this in parentheses on this calculator. So 5 squared divided by 40. Okay, I think I know how to do this on this calculator. It's a little bit tougher. Yeah. Okay, so we're going to take 5 squared divided by 40. Okay. We're going to add it to, in parentheses, 6 squared. Again, these are the standard deviations for each of our populations. Divided by 50, which was the sample size. Alright, so it's 1.345. Alright, so we're going to take 3 divided by 1.345 square root. Enter. We'll go around to 2 decimal places, which ends up being 2.59. Again, have to work with the technology I have. So that's our test statistic. Now, again, we have to reject if somehow it's less than negative 2.05 or if it's greater than 2.05. It is currently greater than. So our decision is going to be to reject the null, H0. Okay? And we're going to find p-value, which is taking now our new one, go and find the z table, 2.58 or 59, close enough. So 2 right here, 2.59, which would be 0.492. So with our calculator, we're going to take 0.5, since it's always in half, minus by 0.4952, then times it by 2. And there is our p-value, 0.0096. Awesome. Okay, next. Question 7. A random sample of 10 observers from one population revealed a sample mean of 23 and a sample standard deviation of 4. Already, we probably know that this is going to be a t-chart, or t-statistic thing going on. A random sample of 8 observations from another population revealed a sample mean of 26 and a sample standard deviation of 5. At the 0.05 significant level, is there a difference between the population means? All right. So here, we gotta find our decision. Again, it's a two-tail. We know that from the equal, from this. So we know it's two-tailed, but we're going to state the decision using t-chart. So now remember, to find the degrees of freedom, we're going to add our 2 observations. So we're going to add 8 and 10 together. Okay, and minus 2. So that's 18 minus 2, that's 16. Okay, here's our chart. That's for Z. Here's T. Again, 0.5 is right there in 2. So we're going to be looking for 16. Two-tail. Two-tail. Right there. And violet. Two-tail. 16. Looks like it's 2.12. So that basically means right here is that T is either going to be greater than 2.12 or it cannot be less than negative 2.12. Okay, now it's time to compute the pool. One of the fun ones. Alright, so when we do the pool, first let's get our calculator. Alright. So, with the pool in itself, we're going to do this all in pieces. 10 minus 1. That's our first group. And it's going to be multiplied by 4 squared. Somehow I entered it all. Okay. 10. So 10 minus 1 multiplied by 4 squared. Okay. So again, 4 is their standard deviation. We have to square it. Okay. We're going to add the combo of our second one, which is 8 minus 1 times our standard deviation of 5 squared. Then we're going to divide it, of course, by the addition of our 2 minus 2. So we end up with 19.9375 is the pool estimate of the population variance. So, yay. Now, we have to do the 2 sample unknown. So again, a little bit of fun little thing that we got to do. So we're going to multiply this by 1 divided by 10 plus 1 divided by 8, close parentheses, enter. So that's 4.4859375. Okay. Now we can take our 2 means. So the first one was 23 minus our second, which is 26. Negative 3 divided by 4.4859375. Square root. So we end up with negative 1.416. All right. So now check our t. Is this less than or greater than? We're looking here for this one since it's negative, and it's going to be more on this side, which means it is greater. So we will not reject the HO, or null. So no rejection there. Okay, so that means this is wrong, according to our math right now. So p-value. Okay. So looking for our item, we gotta go to the t-charts. And again, we're going to be looking for negative 1.416. So we're going to be looking for 1.416. And our 16. Remember, our pooled. Okay? So, calculator. So it's going to fall in between these two. Right here. So it's going to be in between 2 and 0.2 and 0.10. Okay? So it's going to be less than 0.20. But greater than 0.1 p-values. They're fun. Okay. Next. A recent survey compared the cost of adoption through public and private agencies. For a sample of 16 adoptions through public agency, the mean cost was $21,045. with a standard deviation of 835. For a sample of 18 adoptions, okay, so already this is our first one. We'll just circle the numbers. Okay, that's all 1, 1, 1. Okay, for a sample of 18, which is 2, adoptions through a private agency, the mean cost is $22,840. Okay, with a standard deviation of 1,545. Assume the sample populations do not have equal standard deviations and use the 0.505 significant level. Okay. All right. So the first one that we get to handle is going to be the degrees of freedom. And remember, this is, we go all the way, it's going to be this fun one right here. This one. Okay, so we're going to be doing that one and this one. All right. So a lot of parentheses about to hit. Okay. So calculator. All right. So parentheses, parentheses. We're going to take the standard deviation of our first one, which was 835. And we're going to square it. That's going to be divided by 16, which is our first sample size. And then that has to be added to now parentheses our second standard deviation of S2, or not S, so standard deviation of 1,545 squared, lots of money there, divided by our second one, which is 18, and then this has to be squared. Okay, so we're looking at a lot right there. Next, after we've done that, we get to divide by our standard deviation. So again, 835 squared. I don't think it's squared. Yeah, I just squared that one. Okay, we got a little problem. Alright, so we're going to do this in Excel. Let's pop up Excel. Alright. So this is going to equal to yen. Actually, we can't. It's a little bit harder. Alright. One more time. So it's the fun part of having the calculators and trying to do them. So in parentheses again, we have 835 squared divided by 16. Put in parentheses, add. Then we have 1545 squared divided by 18. Close parentheses, square that, then divide, put in parentheses again, parentheses, 835 squared divided by, now n minus 1, or wait, no, we divide by 16, so first one, okay, close parentheses, square that, divide by, now 16 minus 1, so 15, okay, plus, they really make this a lot harder than what it should be. Plus now 1545 squared divided by 18, close parentheses, squared divided by 17, close parentheses. So in the end, after you plug in all those numbers, and now your calculator, which is probably a little bit better than the one that's on the computer, should come out to this number, which surprisingly it does. and 26.7. Now remember what degrees of freedom? We round down, so it's 26. So again, as you can already see, the hardest problem, or part of this problem, is doing the degrees of freedom. That's it. Now we can actually go search. So, calculator. Since we don't have a two-tail, there's not a two-tail on this one because they're not equal. So, assume that they do not have equal standards. They cost between the two. So basically, right now, we have where our null. So H0 is going to have mu of the private, which is going to call it PR. It's going to be less than or equal to, that's a bad mu, public. Okay, and that means our H1 is going to have mu of private is going to be, it's going to be, there we go, greater than that. Oh man, that was so bad. P of public. Okay, so there's our two. We're going to reject our null. C. Using our table, we're going to reject the null 1 at the 0.05. And again, since I have 2, we're going to take 16 plus 18 and minus 2. So that's going to be 32. 32. Wait, no, we did degrees of freedom. Yeah, we already calculated degrees of, sorry. For some reason, I'm thinking of the old one. Never mind. Degrees of freedom was 26. It's like that whole degrees of freedom formula kind of got your professor a little bit. But anyway, our degrees of freedom was 26 at the 0.05 is 1.706. So, we're going to reject this if t is greater than 1.706. Okay? So again, that's why we did the big old formula to find degrees of freedom, to know what basically our decision rule is going to be. Now, we get to actually calculate t-value. Which again, since I'm going to use the archaic calculator here, we're going to do the inside first, which is our standard deviation of 1.835 squared divided by 16 plus our standard deviation 2, which is 1.545. Squared. Kind of wish I can correct that. Messed up. So, real quick. go. Divided by 18. So we have that. That is our variance. 176, 189. Okay. So now we can go ahead and do the problem. So our mean cost basically was 21,045 minus 22,840. Okay. Divided by our recently discovered number 176,189.0625 square root. Okay. So we're looking at 4.276. Because again, we have a positive right here. So we got to make it basically positive so we can look at the numbers. So there we go. Is it indeed greater? It is greater. So we're going to reject. Okay. Problem is anytime that we're dealing with a t-value that's positive, we got to make sure our t-statistic becomes positive. Because it's just dealing with that tail. Which again, remember, symmetrically, they're going to be the same. So we are going to reject the null. Whew. Okay. Last problem. And this is dealing with differences. So the following sample information shows the number of defective units produced on the day shift and the afternoon shift for a sample of 4 days last month. They also want p-value. And is the null hypothesis rejected? And then what is the conclusion indicated by the analysis? Alright. This is fun. Alright, so first thing we gotta do is, of course, find our t value. Because we need to know if we're going to reject. Alright, so we gotta start doing some numbers here. Alright, let's get our Excel going. Remember, this is all based on differences. Okay, going. Okay, guess we're using that one. Let's get rid of all this. So we have 10, 12. Somehow that's a decimal. That's fine. 15, 19. That was for a day shift. Afternoon shift at 8, 9, 12, 15. Okay. So difference is going equal to day shift minus night shift. Let's solve for all four. Alright. So, now that we know this, we need to calculate two things. First off, again, always calculate your mean. So, 12 divided by 4. Okay, equal to 12 divided by 4. So we have 3 right there. And then we got to figure out our standard deviation, which again, we're going to use our powerful new tool right here. Formulas, more functions, statistical. And we're going to do standard deviation of a sample. Okay, there we go. There is our standard deviation. Always by sample because we're dealing with samples. So stdev.s makes it a lot quicker. Okay, so to find our t statistic. Okay, we're now going to take, using our calculator, the classic, the mean, which is 3, divided by our standard deviation of 0.8165, divided by the number that we have, which is 4, standard deviation 2. So this is going to be 7.348. There we go. And now we look at our t-chart to find our p-value. T-chart right here. So we're looking for, again, 7.3484. Now, we actually have to need to know degrees of freedom here. So our significance, which they don't even, well, our degrees of freedom is going to end up being 3 for us. I'm guessing significant level is 0.05 since they don't give us an actual one. Typically we'll default to that one. So here's our t value, because it is 1 till. Okay, and then we find our p value, which is going to be somewhere around way over here. So between 0.01 and 0.001. So really that will tell us already that we're going to need to reject, because it's nowhere near where we need it to be. But let's go ahead. And since our statistic, we're going to reject null if it's greater than this, which indeed it is. It's 7. So, our null hypothesis rejected? Yes. It's going to be rejected. Even, again, critical value is 7.353, yeah. It's less than 0.05 over here. Yeah, because it's falling way over here. 0.005, 0.0005. Even divide by 2, yeah. So, we can conclude that there are more defective parts produced on the day shift than there is on the afternoon shift. That's how it is. Or on the day, yeah. Alright. So that's it. That concludes chapter 11. If you have any questions, you know what to do. So, brave adventurer, off you go on new quest. Enjoy, and I will see you for the next video.